Welcome back to the GATE Academy. I am Shankar Tripathi. Welcome you on the platform of the GATE Academy. So we are here to continue with our lecture series of the new additions to the GATE 2021 syllabus in mechanical engineering. Okay. So this is our seventh lecture in this series. We have already completed 6 sessions before it. You can find those videos on our the GATE Academy English channel. So I would like to request you first that please subscribe the channel if you have not subscribed it yet, so that you will get the notifications of whatever new lectures we are going to upload. And you can also go for seeing all the lectures we have uploaded, all the lectures we have uploaded for the steam turbine and gas turbine, which is a new addition to the GATE syllabus. So in this series, this is our seventh lecture we are going to begin with. So let me first introduce myself a little. So who am I? So my name is, as you can see on the screen, is Shankar Tripathi, and this is the topic we are continuing with. Good morning, everyone. So we are continuing with the steam turbine gas turbine. So guys, my name is Shankar Tripathi, and I am a currently PhD scholar at IIT Roorkee. PhD scholar, you usually call us as research scholar. So I will keep my introduction very brief because this is the seventh lecture in which we are seeing each other. So as I said, if you have not seen the previous lecture, please go for that. So I have completed my MTech from IIT Roorkee, and I have a GATE 8+ years experience in the GATE teaching of various subjects in the GATE Academy. As you know that the GATE Academy is having 50+ centers across India. Okay. So as far as GATE is concerned, so I have ranks in GATE 2014 and GATE 2015. Okay. So in GATE 2014, my marks were 65.66, and my rank in GATE 2014 was 916. While in GATE 2015, my marks was 77.02, and my All India rank was 643. So this is a brief introduction about me. Now we are going to continue with this lecture series. So here you can find the list. Here is the list of what we are attempting to do in this lecture series. So we have completed till this part. And today we are going to begin with the reaction turbine part. But before that, some impulse turbine discussion. Is good morning, Somnath. So some impulse turbine discussions was left. So firstly, we will do that, and then we will move to the reaction turbine part. Okay. So let us continue with our lecture. So we are going to continue with our lecture. Just wait a second. Okay, so here we go. So till the last class, till yesterday's class, what we have seen, till the last session, what we have seen the introduction of the steam turbine. Okay, how steam turbine, what we are studying in here, what is the new addition to the GATE syllabus, what was always there in the GATE examination, and what should be the approach of studying all these things. Okay. So firstly, in the first class, we have seen the introduction of a steam turbine, and we have established a fact that the steam turbine is nothing but the combination of the nozzle and the moving blade. Then in further lectures, we have seen about the nozzles. Okay, how should be the design of nozzle? What is the effect of Mach number on it? So kind of compressible flow we have completed in this series only. So if you are wishing to watch the compressible flow session also, that you can refer this series, you will get 90% of what compressible flow is from this lecture series. Okay. So in the previous 2 sessions, we have started the impulse turbine, and in the last session we have seen how to draw the velocity diagram or velocity triangle of the impulse turbine, and we have derived the equation for maximum efficiency of a impulse kind of steam turbine. Impulse kind of steam turbine. We have also seen in the previous section that how we do the velocity compounding and how we do the pressure compounding, that is Rayleigh turbine and Curtis turbine. Okay, so all of this we have covered in the previous session. So if you have not watched the previous session yet, please go and watch it, then watch this video. You will be, good morning Bharat, so you will be able to understand the things more nicely only when you see all the lectures. Okay, so in this session we have seen, in the last session we have left the last session at the maximum efficiency of the impulse turbine, right? We have left the lecture last session at the maximum efficiency of the impulse turbine, and we had solved a few examples as well in the previous session. Okay, just the session before this session. Okay, so here we are going to continue from that, and let us see another kind of efficiency, that is gross stage efficiency. So in the previous lectures we have seen that we sometimes have to do the staging. We sometimes have to do the staging of impulse turbine. So now we are going to see the term gross stage efficiency. What do we mean by gross stage efficiency? So gross stage efficiency we can say is the, let's see. So gross stage efficiency we can say as the actual, or we can define it as the actual work done in a stage, the actual work done we can say it as the actual work done in a stage divided by, so what is efficiency in general? Actual upon theoretical. So how theoretical, what we can say, the actual total isentropic enthalpy drop, the total isentropic enthalpy drop. Okay, this is what do we mean by the gross stage efficiency. This is what do we mean by the gross stage efficiency of a impulse turbine, of a you can say of a steam turbine. So as we have established in the previous lecture, what is the average, what is the actual work done we get? So actual work done we get is m dot, now see very carefully, actual work done we get is m dot VW1 plus VW2 plus VW2 into U, and what is the total isentropic enthalpy drop? So this is what we can call as delta H, and let's say isentropic. So gross stage efficiency, what gross stage efficiency is trying to tell you, so as you are aware, when we are doing some staging, so there must be some loss. So what is the actual enthalpy drop? What is the actual enthalpy drop due to which we are getting some work? So we are saying this relation we have derived in the previous session, that in a blade we have this much blade power. This is nothing but we have seen the blade power, the actual blade power. We have established these equations in the previous lecture only. So this is our blade actual power. Okay, and this is our, we can see, isentropic enthalpy drop. So So the gross stage efficiency, we can say that m dot VW1 plus VW2 into U. So if you remember, those students alive can respond to me. If you remember from the last session, we have derived this relation, nothing new in it. And let's say if I divide half m dot v1 square, if I divide half m dot v1 square and multiply half m dot v1 square, will there be any difference? Will there be any difference in the equation? Will there be any difference in the equation? So certainly not. We have multiplied and divided. We have multiplied and divided. We have multiplied and divided the same thing only. We have multiplied and divided the same thing only. So there is no difference. So there is no difference coming in the final relation. So if you remember, this what we called in the last session, this was used to be what? Can anybody in the live lecture tell me? So this was our diagram efficiency. And if you remember the previous session, this was our nozzle efficiency. Okay, this is what? This was our nozzle efficiency, and this is our diagram efficiency. So can we say that our gross stage efficiency? Can we say that our gross stage efficiency is nothing but the product of diagram efficiency and the nozzle efficiency. So if you have to find the gross stage efficiency, which means efficiency in general means what? In general means what outcome, what is the ratio of output to input you are getting. So in a stage, how efficiently you are able to convert your enthalpy drop into useful rotation of your blade. We are seeing it here. In the useful rotation of your blade, we are seeing it here. So we have a new formula. You can take note of it. So we have a new formula. So if our gross stage efficiency is asked to you, what you can do, you can go and find it by multiplying diagram efficiency with nozzle efficiency. This diagram efficiency and nozzle efficiency expression we have derived in previous session. Yes or no? We have seen this nozzle efficiency and the diagram efficiency. Okay. So let's say now very important thing is coming up. So a numerical can be asked from this part. So let us introduce now the carryover coefficient. Okay. So we will call it as rho. Okay. So we are going to derive the expression for carryover coefficient. So what does carryover coefficient mean? So it come into play when you do the staging. Okay, when you do the staging. In the last lecture, we have seen how to make the velocity diagram and everything. And this lecture, we are going to go deep into this staging thing. Okay, what is happening in between stages and all. So this coefficient, this carryover coefficient, will come into picture when we do the staging of a turbine. Okay, so we have seen. Let us take up example of Curtis turbine. So velocity compounded turbine. Let's say we are taking an example of. We will understand this with the help of a Curtis turbine. So what happened in Curtis turbine? What we have seen in Curtis turbine. If you remember, those who are live can respond to me. So we had a moving blade. the first row of the moving blade. On the first row of the moving blade, the velocity, we entering velocity of the steam. I am here not making the velocity triangle. Try to listen to me, try to understand the point. Here I am talking about the steam velocity. I am talking about the velocity of steam. So we are not making the velocity triangle here. Just try to listen to me. So I am trying to develop the flow of the steam, that how it will flow. So this is the first moving blade. Let's say moving blade. This is the first moving blade over which we have only one nozzle in the Curtis turbine. We have seen. So over which the velocity is entering at V1 velocity. So this is the absolute velocity. This is the absolute velocity of the steam. This is the absolute velocity of the steam as we know it. This is the absolute velocity of the steam as we know it coming out from the nozzle. So from the nozzle, it will come to the moving blade 1. So we will make the velocity triangle and everything, and it will exit. We call it as V2. It will exit with a velocity of V2. Say yes or no. It will exit at a velocity of V2. So now let's say we have a fixed blade. Because in Curtis turbine, a moving blade is followed with a row of fixed blades. Say yes or no. Say yes or no. Say yes or no. You guys can respond in the chat. So now this is the first row of the fixed blade. Okay. Now tell me when steam moves from this moving blade to the fixed blade. Now tell me, Harsh, V1 and V2 are the absolute velocities. If you have seen the last session, V1 and V2, V1 was the absolute velocity at the entry and V2 was the absolute velocity at the exit. V2 was the absolute velocity of the exit. Okay. So whenever we call V1, V2, we refer to the absolute velocity of steam, right? So now this steam from this moving blade, on this moving blade, steam from exiting from this moving blade now will go to this fixed blade. But what happens? Let the entry to this fixed blade is V1 dash. Let the entry of the steam to the fixed blade is V1 dash. Okay. So from this point to this point means from the exit point of the first moving blade until it reached the next row of the blade, in this region, this carryover coefficient comes into play, because as you know, the steam is traveling from one place to another place. Let us understand in an easy way. So if it is traveling from one place to another place, good morning, Sudhir, one place to another place, so there will be some losses of kinetic energy, as we know. Okay. If steam is traveling from one place to another place, so there will be some loss of kinetic energy. So this carryover coefficient is a representation. This take care represents the loss of energy. Represents the loss of kinetic energy, represents the loss of kinetic energy from one stage to other, Okay. So when our steam travels from one row of blaze to another row of blaze, there will be some loss of kinetic energy. As you can understand, due to the surrounding things, due to the friction present in the actual environment, there will be some loss of kinetic energy. Okay. So this carryover coefficient will tell you about it. So let's say our rho is our rho is, so it is the rho is, so we will define it as v1 dash square upon v2 square, v1 dash square upon v2 square, and this rho is, this carryover coefficient is less than 1, this less than 1. So as we have said, from this point, let's say we are using highlighter here, so from this region to this region, when the velocity reach from this point to this point, there will be some loss of kinetic energy. There will be some loss of kinetic energy. So definitely the velocity of steam, is going to get decreased, Okay. So although what happens, although the steam leaves the first row of moving blade with a higher velocity, but it cannot reach the next row of the blades with that velocity only. There will be some loss of velocity. So generally the value of this carryover coefficient is between 0.9 to 0.95. 0.9 to 0.95. Okay. So we will have, from this relation, we can have the value of the inlet velocity to the next stage or next row of the blade if we have the exit velocity of the previous stage. Is that clear or not? Those who are live can respond to me. And I said, as I said, this lecture can only be understood when you have seen or when you have attended the last sessions, because we are studying in continuation of it. Okay. If you want to understand all the things, just watch all the lectures. Okay. Just watching one won't do anything. Okay. So see, there will be some loss. This will be more clear with some question. Okay. But for now, so let's say we are doing two-stage Curtis turbine. We are using two-stage Curtis turbine. So in a two-stage Curtis turbine, as I have explained, there will be a nozzle, then there will be a moving blade, then there will be a fixed blade, and there will be a moving blade. As we have established in the previous session, that there is no point of let the steam exit from the fixed blade to the surrounding or to the condenser. There is no point in it. We are wasting our money. So as an engineer, we don't have to do it. So if there is a fixed blade, it must be followed by, if there is a big fixed blade, it must be followed by, a row of moving blade. So let's say we have another moving blade. So now tell me what we have learned about the fixed blade. That fixed blade is striking doesn't happen, change of momentum doesn't happen. Fixed blade is only there to change the direction. Say yes or no. Those who are live can respond to me. So fixed blade, we have established that in fixed blade there is no loss of momentum. There will be only change of direction. The purpose of this fixed blade or guide blade, as I told you in the last class, is just to guide the steam to the next row of the moving blade. So how will it will guide it? So just feel the thing. So the steam is entering from here. So it will follow this path. And will be exited from here. So it will be exited with the velocity of v1 dash. It will be exited off with the velocity of v1 dash, or will there be some difference? So definitely there will be some difference. Because there will be some losses, as we have seen yesterday also, that there is a blade coefficient. So while the steam flows through the blade, there will be some losses associated with this flow. There definitely will be some losses associated with this flow. And the velocity decreases. And for that, we had this we had this, if you remember, for that we had this blade coefficient seen in the last session. Yes or no? We had this blade coefficient for that. We had this blade coefficient for that. So in the fixed blade also, there will be some loss of velocity due to the passage, due to the flow of the steam. So as I said, in practical working condition, things are not ideal. So that is why we are putting this coefficients over here. So there will be some loss of velocity. There will be some loss of velocity in the fixed blade part also, but that is not much, as we have seen yesterday also. The value of k is nearby 0.9, 0.95, somewhat like that only. Okay. So now where will the carryover coefficient come into picture? So now the steam is here and it has to reach here. It has to reach here. So here, who will place role? Here, who will place role? So now at this place, carryover coefficient is again going to place role. Carryover coefficient is again going to place role. So it will be equal to, so let's say the entry to this moving blade is, V1 double dash, V1 double dash. So how will you apply the carryover coefficient here? So you will say that carryover coefficient is V1 double dash square upon V2 dash square. As I explained that the steam leaving with the velocity from the previous stage won't reach the next stage of the blaze with that velocity only. There will be some loss associated with in between this travel of steam from one blade to another blade. Travel of speed from one blade to another blade. So from this fixed blade, it exits with the velocity, with a higher velocity, but it do not reach the moving blade with that same velocity, but reaches the moving blade with somewhat less velocity, and that is compensated by this carryover coefficient. So what we have from this discussion, it might have been understood to you. Yes or no? Yes or no? Yes or no? So V1 dash from the first stage, if you see from the first stage of moving blade, the steam left with the velocity of V2. But the entry velocity to the fixed blade was less. And the carryover coefficient was come into play. During the flow over the blade, this V2 dash was less than V1 dash, because as this flows over here, there will be some loss of velocity. Okay, so it is compensated by the blade coefficient. Now, from this fixed blade, the steam is exiting with a velocity of V2 dash. But it can't reach the moving blade with that same velocity, and there will be some loss as well. There will be some loss again here, which is represented by the carryover coefficient, and V1 dash will come out to be less than V2 dash. V1 dash will come out to be less than V2 dash. Is that clear or not? Is the play of carryover coefficient understood or not? Yes or no? You just have to follow the flow of the steam. So obviously, when the flow of the steam, if we are talking about after the nozzle, then that loss, whatever has to be happened in the nozzle has happened. Now the steam is coming to the moving blade at a certain velocity, let's say 1000 meter per second. So it can't exit the first row of moving blade with the same velocity. If you say, sir, why not? So if it exits with the same velocity, there will be no loss of momentum and there will be no torque, as we have seen in the previous lecture. Okay. So let's say in the first stage of the moving turbine, first stage of the moving blade, the steam enters at a velocity of, let's say, 1000 meter per second. Okay. So it won't leave that blade. Leave that blade with the same velocity. It will leave that blade with a velocity less than 1000 for sure, because so many things are coming into play. We have relative velocity, we have made velocity triangle previously, everything is there. Okay, so it is not going to get out with the same velocity. So let's say it is exiting at a velocity of 500 meter per second. Now the steam at a 500 meter per second now will go to the next row of fixed blade. So when it will go to the fixed blade, there again will be some loss due to this travel from moving blade to fixed blade. Okay. So for that, we are having carryover coefficient. From one blade to another, we have carryover coefficient. Okay. So now when the steam reaches to the entry of the fixed blade, some velocity has been lost due to this carryover coefficient thing. Some velocity has been lost due to this carryover coefficient thing. Now let's say we have left with 450 meter per second. We have left with 450 meter per second. For example, we are taking. Now this 450 meter per second will be lost. Some extent of it will be lost while flowing to the fixed blade. While flowing through the fixed blade, because of the blade coefficient, because of the blade coefficient, because of the blade coefficient, because this steam is not going to strike the fixed blades. They do not strike the fixed blades. Yes or no? Fixed blade is there just to change the direction of velocity. So some of you might be confused, sir. Previously you were using blade coefficient with the relative velocity, and so there was some technical glitch, I think. So those who are live can respond to me, as I said. So those who are live can respond to me. So as we have seen, as we have seen, as we have seen that, as we have seen that, as we have seen that from the fixed blade part, when the so I was saying previously there was some technical glitch. So I am continuing myself. So I was saying previously that someone may have this doubt. Someone may have this doubt that sir, previously you were using the blade coefficient. Previously you were using the blade coefficient with the relative velocity, and now you are using this blade coefficient. Now you are using this blade coefficient with absolute velocity. So when the blade is fixed, the relative velocity and absolute velocity are the same thing only. So that's why we are using the blade coefficient with the absolute velocity, because here both are same. Here both are same. Understood? Here both are same. Understood? Okay, here both are same. Okay, so what is happening? What is happening from one blade to another blade? From one blade to another blade, from one blade to another blade, from one blade to another blade, carryover coefficient comes into play. And in a blade itself, when our steam moves in a blade itself, when our steam moves in a blade itself, when our steam moves in a blade itself, our blade coefficient comes into play. Our blade coefficient comes into play. Our blade coefficient comes into play. Okay, blade coefficient comes into play. Okay, so from here again, when the steam exits the fixed blade part, when the steam blade exits the fixed blade part, when the steam exits the fixed blade part, it will reach to the second stage of the moving blade. and here again the carryover coefficient will come into the picture. Here again the carryover coefficient will come into the picture. Okay, so I think till this point the play of the carryover coefficient is clear. So on, if I have to summarize it, so from one blade to another blade, carryover coefficient you will apply, and within the blade coefficient you will apply. So this will be more clear. This will be more clear with the help of our question. This will be more clear with the help of our question. So let us take a question and we will solve it in this class. We will solve it in this class. We will solve it in this class. We will have it solved in this class. So this is the question we are having. This is the question we are having. You can go on and solve this question. This is the question we are having. We can solve this question in the class. Those who are live can solve with me. So I am taking a pause here. So tell me, live students, is it clear to you or not? Carryover coefficient, where to use carryover coefficient, where to use blade coefficient. Can you tell me? Is it clear to you or not? Is it clear to you or not? You can respond to me. So this carryover coefficient thing and blade coefficient thing is clear to all of you. Clear to all of you. So now you can solve this question. So it will be, after solving this question, it will be more clear. So those who are seeing the recorded lecture session, those who are seeing the recorded lecture session, those who are seeing this recorded lecture session, they must also solve it here, so that when I will solve it, your concepts will be very, very clear. Okay. If you directly see the solution and do not work by yourself, do not attempt by yourself, the things won't be that clear as they should be. So firstly, please try to attempt this question. Please read the question. So what it is written here, in the first stage, see, there is a little mistake in this question. Okay, let me correct it. So it is like this. In the first stage of turbine, in a two-row velocity compounded impulse turbine, the velocity at the steam at the inlet is 800 meter per second. The blade speed is 150 meter per second. Okay. So they are talking about here the first stage. They are talking about here the first stage of a two-row velocity compounded impulse turbine. So it is a velocity compounded turbine. So which information is given? What information is given to you? So let us, firstly you try, then I will solve it. I will wait. I will take a pause here. I will wait for a few minutes. It's a very good question. From here, all the concept, all the things will be clear to you. Okay. And after this question, we will suddenly move to the reaction turbine. This is the last thing what we wanted to deal with the impulse turbine. So if you see the previous session, if you have seen the previous session, in that we have understood how to draw the velocity triangle and all. So now see, let's say first what is happening. So in a velocity two-row velocity compounded steam turbine, what happens? We have a nozzle. Okay. Nozzle is followed by a moving blade, and then moving blade is followed by a fixed blade, and this fixed blade is followed by a moving blade. This is how a two-row Curtis is. Okay. So what is given in the first stage of a turbine in a two-row velocity compounded impulse turbine, the velocity of steam at inlet is 800 meter per second. So this velocity is at this point, at this point 1, at this point 1. Okay. After exiting from the nozzle, as explained in the previous session. Okay. So let's draw the first stage of the moving blade, or first row of the moving blade. So we can have the velocity triangle of it. We can have our velocity triangle as we have drawn in the previous session. So this was what? This was the VR1. This was the VR1. We have seen it. This was nothing but U1. Okay. This was the V1. If you have seen the last session, this is also common in fluid machinery. In fluid machinery, this was alpha. This was alpha. And it was exiting with a velocity of VR2. It was exiting with a velocity of VR2. Okay. Okay. So let us draw it a little bit more tangent so VR2 we have established that it is always tangent to the tip of the blade. Okay, remember all these things. So very important question it is. So from here everything will be clear to you. So we have also explained in the previous lecture how to make the velocity triangle. So if you are facing any problem, just go through it. Go through it once. Okay, so this is our V1. So this is how the things were happening. In last day. So this angle was alpha. And from this part of the velocities, we can draw the rest part of it. So this much was what? Till this much distance was VW1. This much distance was VW1. All right. This much distance was VW1. This was VF1. This was VF1. We have explained all this in the previous session also. So this was VF2. This was VF2. And this was VW2. This was VW2. Okay. Okay. So we have this VW1, VF1. All the velocity triangle has been made. Yes or no? So now this is the velocity triangle. Let's say this is the velocity triangle. So I just reduce the size of it a bit. Because so as it comes on the same place in the screen. Okay. So I hope you guys also are attempting this question. So till this point we have seen in the last session. Yes or no? Till this point we have seen in the last session that how to make velocity diagram and all. Right? All right. So now this is our velocity triangle. We know the angles in it. This is alpha. This is theta. Okay. This was phi. These were the blade angles. And this was beta. Now tell me. So this was the first row of the moving blade. This is V2, right? Thank you, Harsh. This is V2. All right. This is V2. Okay. So we have seen that our moving blade is moving in this direction yesterday. So all of this we have seen in the last class only. Okay. So what you have to get, what is information is given to you. So let us first see the information given in the question. So in the question it is given that the velocity of the steam at inlet, you can take the screenshot of this. So that we We'll understand how we are taking data. Taking data, correct data is also very important. So in the first stage of turbine, in a 2-row velocity compounded impulse turbine, the velocity of steam at the inlet is 800 meter per second. So what is given to you? What is given to you? So V1 is given to you as 800 meter per second, right? This is what V1 is. Okay, this is V1, entry to the moving blade. And the blade speed is, so U1 and U2, blade speed is given to be 150 meter per second. 150 meter per second. Okay. So in velocity compounded, the blade, the rotor speed we keep constant. Okay. In compounding of turbine, we will consider that all the rows of the moving blade are running with the same velocity. Okay, same velocity. Our purpose will be served only then. So U1 is equal to U2 is 150 meter per second, as we have seen all this in the last lecture, in the last class too. So what we have, so we have blade velocity coefficient and carryover coefficient. So that when we are going to use, we will apply. Okay, let's just write the given data here. So K is equal to 0.95 here. This is our blade coefficient, and rho is also, means carryover coefficient is also 0.95. Carryover coefficient is also 0.95. Okay. The nozzle angle is 16 degrees. So what is the nozzle angle? Alpha is 16 degree given to us. Alpha is 16 degree given to us. And the exit angle of the first row of moving blade, fixed blade, and second row of moving blade is 18, 21, and 35. So let us take firstly the data of the first row of moving blade, because as we are talking about the first row, so let us take the data of first row. So phi is given to be as 18 degree. How? Sir, exit angle of moving blade. So exit angle of the moving blade, we have defined it as 5. We have seen it that it is nothing but 5. So this is all the data given to us, and what we have to calculate. So blade inlet angle of each row of moving blade. So what is required in the first part? First part, we are required to find the value of theta. So this is how we must proceed, blade to blade. So we are firstly analyzing the first row of the blade, then we will go to the fixed blade, then we'll again go to the second row of the moving blade. Row of the moving blade. If you try to do it in once, or you will try to see everything at once, you will be confused, there will be mistakes. So I recommend you just go one by one. So this is all the data given in respect to the first row of the blade. So we are required to find theta, later we are required to find the power. So let us find VW1, VW2, because that is definitely going to be used in the power and the efficiency thing. Okay, so let us find whatever we can find from here. So firstly we have V1, we have this much data. So in order to find theta, let me first find out VF1. So we know what VF1 is equal to V1 sine alpha from the simple geometry trigonometry. We can do it. We already have done it in the previous class. So VF1, can anybody tell me what is the value of VF1? Can anyone could tell me what is the value of VF1? Anyone? So this VF1, we can use our calculator and can find this is 800 into sine 16 degree. So Madhusmita, thank you. You have given me the answer. So it is 220.5. It is 220.5. So everyone who is live, please respond. Then only you will get the maximum benefit out of it. So VF1 we have. Okay. So if I see in this triangle, if I can have the value of this x, this is x. X is what? This much distance I am saying. If we can somewhere find this distance x, we can have our value of theta by using the trigonometric ratio. Yes or no? By using the trigonometric ratio. Okay. So what is this x? This x, as you can see from the triangle, it is nothing but VW1 minus U1. All these things we have done in the previous session as well. Okay. All of this we have done in the previous session as well. So we have VW1 minus U1. So this x is going to be V1 cos alpha minus u. So our V1 cos alpha is what? Our V1 is 800. Our V1 is 800 and our cos alpha is cos 16 and u we are having as 150. It is given to us. So what is the value of this x? Can somebody tell me? Can somebody tell me what is the value of x? And as I said previously also, you can apply different sort of geometry here. No problem, you are going for the same way. So this is coming out to be 619 something as Aishwarya is telling me. So let me take this value 619. So from here can we find the value of theta? From here can we find the value of theta? From here can we find the value of theta? So yes sir, we can certainly find the value of theta. So tan theta is going to be Vf1 upon x. Yes or no? Vf1 upon x. So from here we can have the value of theta. From here we can have the value of theta. All right. From here we can have the value of theta. So Vf1 we are having, x we are having. So theta is coming out to be what? So as Madhusmita you are telling me, it is 19.6. It is 19.6. Okay. So first part of this question. Okay, some portion of the first part we have completed. Okay, okay. Now to move further, to move to the next row, we require V2. Yes or no? Because our steam will leave this moving blade at the absolute velocity of V2. Okay, so we require the value of V2 also. We require this value of V2 also. Okay, so how are we going to do it? So if VR1 we can find, let us find VR1 first. So VR1 is what? So VR1, as you can see from the triangle, and we already have done all this in the last session also. So it is Vf1 square plus x square. Is it or isn't it? So we have the value of Vf1, we have the value of x. So can we have the value of VR1 also? Can we have the value of VR1 please? Anyone? Anyone can tell me the value of VR1? You are following this question, yes or no? All of you? Are you able to get it or not? So what is this VR1? Can someone tell me? Anyone? So it is coming out to be, as you are telling me, it is 657.3 meter per second. Is 657.3 meter per second. All right? All right, very nice. Very nice. So we have the value of VR1. Now tell me what will be the value of VR2. So how do we calculate the value of VR2? We will do VR2 is equal to K into VR1. We will do VR2 into K into VR1. And we have this value of K 0.95. We have this value of K as 0.95. So this VR2 is going to be 0.95 of VR1. 0.95 of VR1, that is 0.95 of 657.3. 657.3. So VR2 is going to be what? It is going to be 624. Very, very good. Very, very good. So it is going to be 624.43 meter per second. Please all do cross check the calculations. Cross check the calculations, as I am not calculating by myself. Okay, I am seeing the comments and writing it. Okay, so this is VR2. So now we have this value of VR2 also. And it is 624.43. It is 624.43. Now tell me this. Will the steam go to the next series of blade with this relative velocity? Some student might have confusion here in future also. This steam is leaving with the relative velocity. No, my dear friend. Steam, we are interested in finding the absolute velocity at the exit of any blade, not the relative velocity. So do not get confused. Okay? Steam is not moving further with this relative velocity, but steam is moving further with the absolute velocity. Okay, so we require this V2 also. So how can we find this V2 thing? How can we find the V2? So we can again apply so many things. We can again apply so many things. We can again apply so many things. So we have this VW2. Let us find the VW2 also. It is going to be used laterly also. So with this VW2 is VR2 cos phi is VR2 cos phi minus u. Is it or isn't it? Is it or isn't it? Okay. So we have phi given to us, VR2 we have calculated. So can we find the value of VW2? Can we find the value of VW2? So VR2 is 624.43, 624.43, and cos phi is given to us as 18 degree. Phi is given to us at 18 degree, and this is minus 150. This is minus 150. So this VW2 is going to be, can somebody tell me? So this is going to be 443.86 as Aishwarya is telling me. Please do check the calculations, and all the units are in meter per second. Okay. So let us also find the VW1 because it is going to be used in the power, in finding the power. So VW1 is also V1 cos alpha, V1 cos alpha. So this is coming out to be, can somebody tell me the value of VW1? We are going to use it in further. V1 cos alpha, V1 cos alpha. What is this V1 cos alpha? Can somebody please tell me? 800 into cos 16. 800 into cos 16. Shall I calculate myself, or any student is going to help me out? So thank you, Aishwarya and Manusmita. You are giving me the answer. So this is 769. This is 769 something. So we have this value of VW1 also. This is gonna be used in finding the power. So VW1 we have. All right, VW1 we have. VW2 we have got. VW2 we have got. And now to move to the another blade, we require our V2. We require our V2. So let's just apply a little more of geometry. So we require V2. We have VW2. Do we have VF2? Can we find this VF2 also? So VF2, yes sir, certainly we can find. So VF2 is VR2 sin phi. VR2 sin phi. So can somebody tell me the value of it also? VR2 is 624.43. So let us take 624, and sin phi is given to be 18 degrees. So it is coming out to be what? It is coming out to be 192.8 meter per second. Do check the calculation by yourself. And also the unit is everywhere meter per second. Unit is everywhere meter per second. So we have VF2 is equal to 192.8 or 9. 8 and 9. Anirban, you are asking, sir, I did not get cos 516. Where cos 516 is written? This is cos 16, my dear friend, not cos 516. This is not cos 516. Cos 16 degree. Nowhere we have written cos 516. Okay, got it? So this is VF2 we are having. Now we are having VF2, we are having VW2. Can we have our V2? Can we have our V2? So yes, sir, we can have our V2 now. V2 is under root of, see this triangle? See this triangle? V2 is, we can find like this. V2 we can find like this, yes or no? V2 we can find like this. So V2 is coming out to be 484 meter per second. 484 meter per second. So this is all what we have done in the previous session also regarding the level turbine. That is the simple turbine that has only one set of moving blade, Yes or no? Yes or no? So what is important things we have obtained from this? So we have this VW1, we have this VW2, and now we are having this V2. Now follow the path of the steam. Now this steam with this velocity will want to go to the first set of the fixed blade, and it is as it is a two-row Curtis turbine. So we have only one row of fixed blade. So fixed blade or guide blade, whatever you want to say, you can say. So it is a fixed blade 1. So now the steam from moving blade 1, or let us make it again. Let us make it again for better understanding. So we have this first moving blade. We had this first moving blade. Okay. From here, from this first moving blade, our steam is leaving at the velocity of v2. Our steam is leaving with the velocity of v2, and it is going to enter the first row of the fixed blade. So as we have established that our steam cannot reach here with the same velocity. So let us say that it reaches to the fixed blade section. With v1 dash velocity. So what will be the v1 dash? So we can calculate the v1 dash by using our carryover coefficient. So it is equal to, carryover coefficient is equal to v1 dash square upon v2 square. So v1 dash square will come out to be, rho we have as 0.95. So it will be equal to v2 square by 2, and we can apply under root over here. So can you calculate it for me? So what is this v1 dash? Can you tell me? What is this v1 dash? So 484 square into 0.95 under root. So it is coming out to be 471.7. Mother Smita, you were giving me previously 459.8. Please cross check your. I have to use this calculator. So v1 dash will be 471.7 meter per second. So now I think the play of this carryover coefficient would have been more clear. Okay. So the velocity leaving the moving blade, the previous set of blade, is at 484, and it is reaching the next blade at 471.74. Now we must follow the path of the steam. And this steam will leave the fixed blade at, let's say, the velocity of v2 dash, because we are calling the exit with 2 and entry with 1 subscript. That is why I am using v2 dash. You can use other notation also, no problem in that. Okay, so v2 dash. So here in this reason I am highlighting what will come into the play. This will be the path of the steam. Steam will deflect, changes path, will not strike the fixed blade. Yes or no? So this reason who will come into play? So our carryover coefficient will come, our blade coefficient will come into play. So v2 dash will be found by the blade coefficient, from the blade coefficient. So we have this v1 dash. Can anyone tell me the value of v2 dash? Please? K is given to be 0.95. So this must be very, very clear to all of you. This must be crystal clear to all of you where to use the carryover coefficient and where to use the blade coefficient. Now tell me. So it is coming out at 448.15 meter per second, as you guys are telling me. 448.15 meter per second. Now, where this steam will go? So it will reach the another set of moving blade. it will reach the another set of moving blade. It will reach the another set of moving blade. Will it reach here by V2 dash velocity? Will it reach there with V2 dash velocity? So what would you say? You would say, sir, no, no, sir, it cannot reach there with V2 dash velocity because the carryover coefficient will come into play from one blade to another blade, and there will be some loss of velocity. And there will be some loss of velocity. So this V1 dash double dash we can calculate like this. It is rho into V2 dash square under root. Okay, so let us put all the values. We have rho, and unless otherwise specified, keep the carryover coefficient as same. Keep the carryover coefficient as same what is given in the previous stage. So carryover coefficient, do not consider that it is changing from stage to stage if no such information is provided to you. So it is 0.95. It is 0.95, and we have our V2 dash with us. So V2 dash is 448.15 square. So can somebody tell me the value of V1 double dash? V1 double dash. So it is coming out to be 436.7. It is coming out to be 436.7. Okay. Okay. So now from here, as you can understand, so many things can be asked. So many things in between can be asked. Someone may feel, sir, this is a very big question. It may not come in GATE examination. So if you solve this question, many small questions will be covered by itself only. So see how now we have reached to the second stage of the moving blade. How we have reached to the second stage of the moving blade. Now, two questions are there. Now, two questions we must have in our mind. Sir, this steam is entering the second stage of moving blade. This steam is entering the second row of the moving blade with this much velocity. Now, what will be the angle? What will be the angle at which it is coming here? What will be the angle by which it is coming here? Now, let's go back to the question. So, what is given? The nozzle angle is 16 degrees. Do not use it here. This is the nozzle angle. Nozzle angle we have used. Nozzle angle. This is by this angle the steam was entering the first row of the moving blade. Okay. Now see. Now read the question again. So this is the exit angle of the first row of the moving blade, the fixed blade, and the second row of the moving blade are 18, 21, and 35. So can we say that this steam is deflected with this angle, let's say alpha dash we may say. This is the exit angle of this fixed blade now. We can say alpha double dash also, no problem. So this is the exit angle of the fixed blade now. So with this angle only, our steam is going to enter the next row of the moving blade. So let us now draw the second row of moving blade velocity triangle. So this is what I am going to do for second stage of the moving blade. So I can copy it, but I am making it again. So that it is very, very clear to you. So now tell me, how do we make the relative velocity triangle? You are aware. So here there must be relative velocity VR1. Here there must be, or previously I used red color, no, for relative velocity. So let us use the red color only for relative velocity. Please try to understand each and everything. By this lecture, your steam turbine, impulse steam turbine will be completed in all the respects. So this is VR1, this is VR1, this is going to be U1, this is going to be U1, and this is going to be what color I have here? Blue, green color. So this is going to be V1. This is going to be V1. Now be careful, my friends. Be careful, students. Be very, very careful here. You have to be very, very careful here. Why? Because this angle, this alpha double dash, Okay, and I am using the subscript double dash for the second stage of the moving turbine. So let us call this also double dash. Let us call this also double dash. Let us call this also double dash. Okay, let us call this also double dash. Let us call this also double dash, because we are doing it for the second stage of the turbine. For the second stage of the turbine, we are doing it. We are doing it for the second stage of the turbine. We are doing it for the second stage of the turbine. Okay. So now if we complete this triangle, we will have we will have we will have this VF1 double dash, and this whole will be VW2 double dash, VW double dash, okay, VW double dash, and this is VR1 double dash, and this was, we are making this X, okay, that we use. And so I think you are very much aware with this velocity triangle. You are very much aware with this velocity triangle. So before making the exit velocity triangle, let us now calculate whatever we can calculate from this. We do require VW double dash, right? Yes or no? So before making the exit triangle, we just calculate everything from this inlet velocity triangle. So we have this V1 double dash. We have already calculated is this 436.7. Okay. Now take note, be careful. We are having this alpha double dash is equal to 21. Okay. How I am saying this? It is given in the question itself that the exit angle of the fixed blade. So how we will get the input data for the second stage of the moving blade? Now I am explaining that. Be very, very careful. So the exit angle of the fixed blade will become the nozzle angle or the entry angle to the next stage of the moving blade. You can tell me if it is clear to you or not. If it is clear to you or not. U1 double dash, as I said, U1 shall be same. So it is 150 meter per second. It is 150 meter per second. It is 150 meter per second. And this is theta double dash. This is theta double dash. So we were required to find this theta double dash in the U is same for all the stages. The velocity of the turbine, the velocity of the rotor is same for all the stages. If not same, it would have been mentioned, but 99% time it is same only. It is same only, especially for two-stage Curtis turbine. Got my point, Aishwarya? So unless otherwise mentioned, you will take it as same, because our turbine is axial flow. No, if you go for fluid machinery also, there you also study the axial flow turbines, na? Like Kaplan turbine, also for example. So there in axial flow turbine, we have this consideration always that U is same. So here also we will consider U is same. So U1 double dash is 150. So from this you can calculate theta double dash. So what will be theta double dash? So let us calculate it very, very quickly. Would you like to do it? Those who are live, will you be able to calculate everything for this turbine? This second row of moving blade. So this is tan theta double dash. It will be equal to VF1 double dash upon X double dash. What was our X? What was our X? What was our X? So VF1 double dash is V1 double dash sine alpha, and X double dash is V1 double dash cos alpha double dash minus U. So U is same, so I am using U only. U is same, I am using U only. So we have this value of V1 double dash, we have this value of alpha double dash, we have this value of alpha double dash, we have this value of U. So you will have the value of theta double dash from here. And as Aishwarya is telling me, thank you very much for responding. So all of you must also respond. Only few are giving me the answers, but all of you must respond. If you make calculations with me, your revision time will be reduced, and you will be able to get all this information beautifully. So it is 31.26. So can we say the first part of the question is completed? Blade inlet angle for each row of moving blade, is it completed or not? Is it completed or not? Is it completed or not? So you can say yes, sir, it is completed because we have theta. So first set of the moving blade, we have theta. So we have the first stage inlet angle of the moving blade, and we have theta double dash. So we have we have we have we have theta double dash. We have theta double dash for the next blade. Okay, so yes, you are asking me, sir, please explain second stage angles one more time. So I will do it. So see, from the first fixed blade, from into the fixed blade, the steam exits with a angle of 21 degrees. So this 21 degrees is the exit angle of the fixed blade or entry angle to the next stage of the moving blade. It can be the exit angle of the fixed blade or the entry angle to the next stage of the moving blade. Okay, so we will have this alpha double dash given in the question 21. You can see the question, it is given in the question. Okay, so alpha double dash we have got. Yes, Tote, you are answering you are questioning it or not? Harish regional, uh, when our electrical subject live classes scheduled, so you can subscribe this the Gate Academy channel, and you will get the notification of it. Don't worry. This subject is mechanical subject is running, so you can subscribe the channel. You will have the notification about the live schedules of electrical engineering. Okay, yeah, yes. So you have got it or not? I hope you have got it. So now our first part of the question is completed. So let's put a tick over here. Now the second part, the power developed when mass flow rate is 4 kg per second. So what would be the power developed? Second part, if we do, so we do not require to make the velocity triangle. That is why that is why I have not made the velocity triangle of exit till now, because why to waste energy? Why to waste energy? We will do it when we require it. We will do it when we require it. If we do not require it, we won't do it. So first let's check we require it or not. Because if the question is till the first part only, we certainly do not require the exit triangle of the next stage of the moving blade. As the exit triangle of the next stage of the moving blade. Okay, so let us see what is the power. So power will be m dot. So what will be the power? Obviously the power produced by moving blade 1 and the power produced by moving blade 2. So if you sum them up, you will have this. Say yes or no. It is obvious, no, that the power produced is the power produced by individual moving blades. So if this much power is produced by moving blade 1 and this power is produced by moving blade 2, you can simply sum them up. So that this is what I have done. So what we have till now, we have our VW1, we have calculated VW2. Let's see, we have VW1 double dash or not. So yes, we can calculate VW1 double dash. So VW1 double dash we can calculate like V1 double dash cos alpha. So can somebody tell me the value of VW1 double dash? We have the value of V1 double dash. So it is, as you are telling me, it is 407.78. So we will require this data to solve the question. So let's just highlight it. See, in these questions, in these kind of questions, we have to know how to handle the data as well. Because so many calculations are required. As you see, so many calculations are happening. So you must arrange your data accordingly. Okay? Arrange your data accordingly. So we have this VW1 double dash. Now we have this also. So let's put a tick mark here. So now VW2 double dash is also required. We have U. So VW2 dash we require. So that is why we have to make this exit triangle also. So we know that this is VR2, this is VR2, this is VR2, this is going to be U2, this is going to be U2, this is going to be U2, this is going to be V2, this is going to be V2, this is going to be V2, and this is going to be sorry, opposite direction. This is going to be VW2, VW2, and this is going to be VF2. All right, VF2. So this is 5. This is 5. So I am using the subscript of double dash. I am using the subscript double dash here. So it is double dash, it is double dash, it is double dash, it is also double dash, and it is also double dash. So same way I have made, yes, 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 you will get. Don't worry. You won't be able to exhaust the rough papers given to you. You will be given a pad in GATE examination, and I don't think you will be able to fill it up. I have never heard, frankly speaking, I have never heard some students saying that, sir, I would have got all India rank 1, but my paper, rough paper was finished. These are all the excuses. Okay. So you will get the rough paper, rough work, everything you will get. Everything you will get. And if you are getting the paper right, if you are having the knowledge of the questions, so you will arrange it. Don't worry about this rough paper and all. You do your preparation well, everything will be in order then. If don't do your preparation well, then the rough paper will be insufficient. Your pen ink will be over. Everything will happen. Your computer will stuck. Every here and there things will happen. So don't talk like that. Okay, so we are having to find this VW2 double dash. We are having to find this VW2 double dash. So can we find it by using this velocity triangle? So yes, certainly we can. Certainly we can. So this is VW2 double dash. So let us calculate that. VW2 double dash. So we are going to calculate it. So it is what? It is what? Can we write VR2 double dash cos phi minus U2, and U2 is same as U. U2 is same as U. Yes or no? Yes or no? So VR2 double dash is what? VR2 double dash is K times VR1 double dash. K times VR1 double dash. Okay, so can we find VR1 double dash here? Again, we have to follow the same thing. So this VR1 double dash is, under root VF1 double dash plus X double dash whole of a square. What I am mentioning this X to be, this is X double dash, no? We use it earlier also. So can you tell me VR1 double dash, what is the value of VR1 double dash coming out to be? Can anyone tell me? VF1 we are having this, X we are having this. I hope you can calculate all these things and can tell me VR double one dash value. VR1 double dash value. Can anyone could tell me please? Anyone? So it is coming out to be 301.55. I hope every one of you is following the series of development or the calculation. So here we are having this VR1 double dash. So we can have our VR2 double dash. So we have the value of K is equal to 0.95. So it is VR1 double dash, that is 301.55. I am making it a little bit faster because all this we are seeing the fourth time. In the previous session, we have done 2 questions of velocity triangle. Okay, we have done 2 questions. This is a combination of 2 questions because there are 2 stages. So firstly, we did it here. All this we have did it here, and all this we are doing here also. So can anybody tell me the value of VR2 double dash, please? VR2 double dash. Anyone? So it is coming out to be 286.5, let's say. 286.5. So this is the value of VR2. Let us highlight it. So this is VR2 double dash. This is VR2 double dash. This is VR2 double dash, as you can see it. This is VR2 double dash. Don't get confused here. Don't you get confused. Okay. Okay. So now VR2 double dash we are having. VR2 double dash we are having. So it is 286.5. It is 286.5. And we are having the value of phi given in the question. See. Now you will say, sir, phi, where is phi? So see. The nozzle angle is 16 degrees. The exit angle of the first row of moving blade, fixed blade, and second row of the moving blade. So exit angle of the second row of the moving blade is given as 35. Is given as 35. So we have this cos 35, and we have the value of u as well. So from here we can find the VW2 double dash. VW2 double dash. So it is equal to what? Can somebody tell me please? So it is 84.69. Someone of you has already told me this. So I am using 84.69 here. So now can you have the value of power, as we have everything we require? M dot is given in the question as 4 kg per second. Yes or no? Yes or no? So do we require to find V2 double dash? Now hold here. Have some patience. Hold here. Now do we require? Now tell me, do we require to find V2 double dash here? Do we require thing? So we do not require to find V2 double dash here, because we would have required it if there is another set of fixed row. Okay, then we would have applied the carryover coefficient, and we'll see that what velocity reaches to the next stage of the fixed blade. Then we would have applied the blade coefficient over this fixed blade, and we would have found the velocity of exit at the fixed blade, and then again we would have applied the carryover coefficient to find that at what velocity steam would enter the next stage of the moving blade. Okay, so this plays clear to you or not, every one of you? So if there are more stages, let's say we have used only one fixed blade, so if we use two fixed blade and three moving blades, would you be able to do it again and again? Would you be able to do it again and again? So this is very unlikely. Because this much big question do not come in GATE, but anything in between can be asked. You may have given the exit velocity of the third stage of moving blade directly, and from there you would have asked the velocity of the next fixed blade or moving blade. Would you be able to do it? Is everything crystal clear? Are you liking this lecture or not? Please comment in the comment section. And if you are liking it, please share with your friends. Please subscribe the GATE Academy channel also, so that we can have all this discussions, all this good technical discussion videos. Because as you are seeing, if anybody is seeing this video in the GATE Academy channel, we do not talk anything else, or majority of things we are talking about what is required, what is useful for you, without wasting the time of anyone. Okay, so we can put all this value in the power, and I believe all of you now can find the power for me. M dot is given to be 4 kg per second. This is given to us. So can someone tell me, put all these values, can someone tell me the power? So it is coming out to be 1022 kilowatts somewhat. It is coming out to be 1022 kilowatts something. It is coming out to be 1022 kilowatts something. Okay, got my point? So we are having the power also. Yes or no? We are having this power also now. All right, we are having the expression of this power also now. Now, what is the last thing? We have calculated the second part of this question as well. Now, what is the combined efficiency of the turbine? They are asking. So, what is the combined efficiency means? What? The overall efficiency of all this thing. So, what will be the overall efficiency? Can someone calculate me? So, overall efficiency is what? The output upon input. So what is the input to this Curtis staging? So the input was half m dot v1 square, because as I said here, or we have seen in the previous lecture also, that this is what is a Curtis stage. This much is a Curtis stage. Na? Don't get confused. You are asked about the efficiency of this Curtis stage. This is our Curtis stage. Yes or no? So here we have the energy, what energy we are having here. So at the exit of nozzle, all the energy has been converted into the kinetic energy. So at this point, we are having this much of kinetic energy, and this is going to get utilized in all these things. This is going to utilize in all here. Okay, so what is the input we are having? Efficiency is output upon input. Okay, do not make some new formula for it. In some books, a new formula is given to it. I don't know why. So if you can find the power, you can have your input, that is entry. At the time of entry, what energy you had. From that energy, you created this power only. No. So your efficiency is output upon input. So you place all the values you are having. Can anyone tell me the efficiency? Just remember to put 10 to the power 3 here also, because you are going to use this. If you are putting the velocity in meter per second, you have to use the power as what? General dimensional thing. So V1 is how much? V1 is 800. V1 is 800. So efficiency is going to be, if you calculate from here, it is going to be 79.84, as someone of you is telling me. So this is gonna be the efficiency. So do we have any confusion till now? Do we have any confusion till now with this question? If any doubt was there in the previous section of the Curtis staging, that's why we doing the Curtis staging, why we are going to do the Curtis staging and all. Although I explained in the previous session also, but with this question, everything would have been very, very clear that how to operate in the compounded kind of turbines, impulse turbines. So everything is clear. If till now, you can give me a thumbs up in the comment section, and you can please share and subscribe the GATE Academy channel. You can please share and subscribe the GATE Academy channel. So with this, we have completed the impulse turbine part. Okay. So in impulse turbine, as I said, we have analyzed nozzle separately, and now we have analyzed the moving blade. On the moving blade, one of your open channel flow is not in GATE syllabus of mechanical engineering. Okay. Open channel flow is in fluid mechanics, and it is exclusively in the syllabus of civil engineering. So if you are a mechanical engineer, you don't have to study open channel flow as far as GATE examination is concerned. All right. If you are a civil student, then you may learn open channel flow. Okay. So now we have completed impulse turbine in all the respects. Firstly, we have analyzed the nozzle, how should be done design of the nozzle, how to find the areas and all, critical conditions, sonic, everything. Harsh Sumala, the exit angle of the fixed blade is equal to the nozzle angle of the next moving blade, not the previous one. The other one, the one which is after the fixed blade. Got my point? Okay. Because in the first lecture, if you have seen, I said this nozzle angle or fixed blade angle are the same thing. So you can call alpha as a nozzle angle or fixed blade angle or a guide blade angle. It doesn't make any difference. Okay. So let's say come here. So exit angle of this fixed blade. This exit angle of this fixed blade will be the entry angle to this moving blade, or the guide blade angle or the nozzle blade angle of this moving blade, not this moving blade. Okay. This moving blade nozzle angle will be decided by this. Okay. So if we have after this moving blade, if we have, let's say, another fixed blade, so the exit angle of this fixed blade will determine, let's say the exit angle of this fixed blade is phi. So here alpha is gonna be phi. Let's say the exit angle of this fixed blade is phi dash. So alpha here is going to be phi dash. Okay. Got my point. Now, as I was telling, in impulse turbine section, we have exclusively covered the nozzle part, which is also common for compressible flow. So if you want to understand the concept of compressible flow as a mechanical engineer, you can go for it. Also. And with all respect now, whatever is required for GATE 2021 syllabus edition, the impulse turbine is completed in all respects. So now let's just quickly complete with this reaction turbine. Just go with this reaction turbine. And here, as you have understood mostly all the concepts, so we will not go very much deep into this, but we will see what is only required, because this is same velocity triangle and all is the same as you see in fluid machinery also. So here, first thing, the first confusion you may have, I have established in the first lecture itself that steam turbines are axial flow turbines. Steam turbines are axial flow turbines. Okay. So tell me, do we need to do this discussion again for gas turbine? The same discussion is there in gas turbine. So we are not going to do it again in gas turbine. Okay. So somebody may feel, if see the gas turbine video, somebody may feel, sir, in the gas turbine video, sir is telling the old things only. So this also have become old now, na? If we are going to analyze the blades of gas turbine, that is also an axial flow turbine. So the same chronology will happen, same thing will happen. So you can do it by yourself, no need of repeating it again and again. All right. So now we are going for starting the reaction turbine. So I have established in the first chapter, I told you in the first session of this lecture series itself, that the steam turbines are axial flow devices. So if you talk about a reaction turbine, axial flow reaction turbine, so as you can refer Kaplan turbine of fluid machinery, you must have heard the name of Kaplan turbine there. So there also U1 is equal to U2. So don't get confused. In reaction turbine, there is radial reaction turbine in which U1 is not equal to U2. But in axial flow reaction turbine, U1 is equal to U2. U1 is equal to U2. So let's just quickly finish with this reaction turbine. And in the next lecture, we will see the reheat factor and all. And something if left if of reaction turbine, then we are going to see with that. And then we will conclude this steam turbine. We'll see some theory part also, means governing critical speed, what is that all of with respect to steam turbine. We are going to see that too. But for the numerical part, as far as concerned, this reaction turbine is going to be the last discussion. So our next session will be almost the last session for steam turbine. Okay. Maybe in the next session, we will be able to discuss the governing and critical speeds of the steam turbine. If not, we will discuss in the next lecture. And today, after the next lecture, your next live class is on Monday. Okay, on Monday, not on Sunday. Okay, so you may revise all the live students, you may revise everything by this Sunday, and we can meet again on Monday for the remaining part of this lecture series. Okay, very quickly, I will finish with this gas turbine thing. Very quickly, I will do it. So do come in the next sessions also. So reaction turbine, as I said, it is an axial reaction turbine. So first thing is that velocity must be same. So what we have seen in reaction turbine in the introduction part, the reaction turbine in the introduction part, that we have some fixed blades. All right, we had some fixed blades. We have moving blades. So in reaction turbine, what we had? For more details, please go for session number 1 of this lecture series. So we had this fixed blade, we had this moving blade. Okay. So quickly let's go through what was happening. So let the pressure of the steam entering this fixed blade was P0. So there will be a pressure drop in fixed blade. There will be a pressure drop in fixed blade. Okay. Then again, there will be some pressure loss in moving blade. I told you how reaction turbine is different with the impulse turbine, because in moving blade also we have the pressure drop in reaction turbines. While we talk about the impulse turbine, the pressure remains constant in this moving blade part. Now in this fixed blade part, again the pressure will decrease, and this moving blade part, again the decrease of pressure will be there. So we have established this in the first session also. I am telling you this again, that in reaction turbine, the drop of pressure also takes place. Drop of pressure also takes place in the moving blade also. The drop of pressure takes place in the moving blade also. So what about the velocity? What about the velocity? What about the velocity? What going to be about the velocity? So we have entry velocity as V naught. So we have seen in fixed blade the velocity will increase. In the moving blade the velocity will decrease. In the fixed blade again velocity will increase, and in the moving blade again it will decrease. In the moving blade again it will decrease. Okay, in the moving blade again it will decrease. Now somebody may have this doubt, sir, in the moving blade the pressure is decreasing, so how the velocity can decrease? So I told you this with respect to nozzle, that in nozzle when pressure in decreases the velocity increases. It is not true everywhere. It is not true everywhere. Okay, if the pressure energy, how we in general, how we say that, sir, if the pressure is decreasing the velocity must increase, because what the logic behind it? Because the pressure energy when get changed into kinetic energy of the steam, then it will then it will then it will change into the kinetic energy of the steam. Okay, but here this pressure drop do not change into this, the loss of pressure energy do not change into the kinetic energy of steam. So the kinetic energy of steam do not change. Kinetic energy of steam do not increase. It will decrease. Okay, it will decrease in the moving blade part. Okay, so in the fixed blade, what is happening? We have explained all this in the first session. In the fixed blade, what is happening? The velocity, pressure drop is there. Velocity is increasing. In the moving blade, with this high velocity, moving blade with this high velocity, steam is entering the moving blade. So there is some impulsive effect due to this high velocity, as we have seen in impulse turbine. But there will be some reaction effect also. Reaction effect means due to this pressure energy. See, now try to understand this. Let us understand this fact. I have highlighted these 2 points. Just focus here. I have highlighted these 2 points. Just focus here. So let us call this point as 1. Okay. So at this one point, the students who are live here can respond to me. At this one point, we have high velocity of the steam, and we have also some pressure energy of the steam. Of the steam. So at this entry to the moving blade, our steam is entering with both kinetic energy and pressure energy. So now this high velocity steam when strike to the moving blade, due to the loss of momentum, there will be some impulsive effect, as we have seen in the impulse turbine. And it will help, or it will do some work on the blade, and blade will rotate some of it rotate by the impulsive effect due to high velocity. Now as the flow of steam takes place in the moving blade, will take place in the moving blade, this pressure energy will reduce and will give you the relative velocity. This pressure energy will give you the difference of relative velocity, which will help the impulsive effect, which will help the impulse energy even more, and the blade will be rotated with even higher speeds. So most of it is explained in the first session also. So what will be the work done? In a steam turbine, in a reaction turbine? What will be the work done? Now just listen to me. So this point we have entered with V1, and let's say we have exited with V2, and here also this is 2. Okay, so what will be the work done? So we have entered with a high velocity. We have entered with the high velocity. So we have V1 square by 2 kinetic energy at the entry. Kinetic energy at the entry. So when your steam leaves the moving blade, its velocity will be reduced. So this is what impulsive effect. This is what impulse we talking about. We were talking about the in the impulse turbine. We were talking about the impulse in the impulse turbine. Right or wrong? Right or wrong? So there will be some impulse also in here. There will be some impulse also in here. Yes or no? There will be some impulse also in here. Right or wrong? There will be some impulse also. Yes or no? But there will be some pressure energy also. There will be some pressure energy also. So let's say at this point we have relative velocity 1, and at this point we have relative velocity 2. Relative velocity 2. So what will this pressure energy will do? Pressure energy will change the will affect the relative velocity. If you see, if you have followed the impulse turbine discussion, there VR1 was equal to VR2. Only losses we were considering was due to friction and all. For that, we were using the blade coefficient. But if we consider the blade to be smooth, there, VR1 was equal to VR2 in impulse turbine. But here, due to this pressure energy, VR1 will not be equal to VR2. And what play this pressure energy will do is that VR2 will be greater than VR1. VR2 is greater than VR1. So the relative velocity is nothing but the pressure energy will affect the relative velocity. So the relative velocity will give you. So we will write like this: VR2 square minus VR1 square by 2. So this is the effect of this pressure energy on the blade, and we generally call it as reaction. That is why these turbines named as reaction turbine. These turbines are named as reaction turbine. So even this reaction turbine, it is not purely reaction turbine. It is not purely reaction turbine. We are having some impulse effect in it. So can we say it? Can we say like this? That this work done we are obtaining because of 50% because of impulse and 50% because of reaction. So that is why it is called as 50% reaction turbine. It is called upon as 50% reaction turbine, or you also know it as Parsons turbine. So 50% reaction turbine or Parsons reaction turbine is the working turbine we use in general. Okay, working turbine we use in general. So from this discussion, if you want to guess what would be the 100% reaction turbine, if you want to guess that what could be the 100% reaction turbine now, what could be the 100% reaction turbine now, what could be the 100% reaction turbine now? So you can conclude, sir, if in a reaction turbine there is no impulsive effect, if in a reaction turbine there is no contribution, yes, Madhu Smita, we are considering that 50-50%. That is, according to that, we have managed these stages. And if not, see, in a Parsons turbine, this 50-50% happens. If not Parsons, this may vary. If not Parsons, this may vary. If Parsons, then this is happening. If Parsons, let me make myself clear. I am talking here about a general reaction turbine, but if it is to be Parsons turbine, this is what about the general reaction turbine. But if it is to be a Parsons turbine, if it is to be a Parsons turbine, if it is to be a Parsons turbine, then the reaction will be 50% and impulse will be the 50%. Impulse will be the 50%. Okay, impulse will be the 50%. Got it? Got it? Now, Harsh, you are saying everything is clear, but why VR2 is greater than VR1? So see, this part is common in fluid machinery also. That is why I have not proved it. Otherwise, it can be proved also. But listen to me. Now see, relative velocity in general is what? Absolute velocity of steam minus absolute velocity of blade. Is this in general? In general, relative velocity is the difference between both. With some angles are there, that is different thing. But absolute velocity of steam minus absolute velocity of the blade is somewhat the relative velocity. Yes or no? Yes or no? Now, as as this steam will strike the moving blade, its absolute velocity goes on decreasing. As you can see from this diagram, its absolute velocity goes on decreasing, but the velocity of blade will goes on increasing due to this pressure energy changes. Due to this pressure energy changes. Due to this pressure energy changes. So ultimately, what is going to get happen? Ultimately, what is going to get happen? That absolute velocity of the steam is decreasing, but absolute velocity of the blade is increasing, and the rate of increase of the absolute velocity of the blade is very much than the rate of decrease of the absolute velocity of the steam. So hence the relative velocity will increase. So hence the relative velocity will increase. Got my point or not? Got my point or not? Okay. So now don't have any confusion here. Don't have any confusion here. So let us say, now let us, if somebody is going to have some confusion, this might be X% and this might be Y%. All right. All right. So if this impulsive effect percentage is 50% and this percent is 50%, then you will call it as Parsons turbine. Got it, Madhusmita? Okay. Otherwise, it is a general reaction turbine. Okay. So now 50% reaction turbine and Parsons reaction turbine is clear to you? Or why we use this term 50% reaction turbine? Is that clear to you? Is that clear to you all? Yes or no? Is that clear to you all? Tell me yes or no. So if I say there is 100% reaction turbine, we generally use this Parsons turbine. Why we generally use this Parsons turbine? I will clear it in the next session, because now time is going to get up. So we are going to cover it in the next session also. So 100% reaction turbine means what? What do we mean by 100% reaction turbine? Any guesses? So I think all of you can guess. So if 50% reaction turbine means that the contribution in the work done of the reaction is 50%, then if the contribution of reaction is 100%, then it will be 100% reaction turbine. It will be the 100% reaction turbine. Okay, so 100% reaction turbine, there is no impulsive effect, so it is Hero's turbine. Hero's turbine. Okay, okay, okay. So it is used centuries back. It was developed in the time of Romans, Greeks. Okay, it was developed first clue of this Hero's turbine can be seen back into some before Christ time. So 100% reaction turbine is possible, absolutely possible. No problem in that, but it is not recommended. It is not recommended. If you see 100% reaction turbine or Hero's turbine, if you see 100% reaction turbine or Hero's turbine, it is having no blades. It is having no blades. Okay. You can make it at your home as well. Some people are doing it. Some people are making this kind of things in their BTech projects also. BTech projects also. Okay. So this is possible. There is no blade in it. No blade in it. But there is high axial force happening in it. High axial force happening in it. Okay. Okay. So it is kind of a steam is going to flow from a nozzle and will strike some rotational kind of thing, and it will get rotated. It will get rotated. So it's a very basic first kind of, or you can say this is the first ever steam turbine. This is in the history. It is also the first developed or first working steam turbine. It was the first working steam turbine. But with the development, this is obsolete now. With the development, it is obsolete now. And in this, there are high axial thrust. Okay. Okay. So from this point, we will continue in the next lecture. So in the next lecture, what we are going to do, let me write the heading of the next lecture here itself, that we are going to analyze this. We are going to analyze this. So the next lecture is in the is will start. The next lecture will start from 1 p.m. today. So those who want to attend live may join us, and those who are watching this video, please watch all the lectures of this lecture series. Then you do not have to do anything else, just solve few more numericals, and you are ready with this new syllabus. Okay, so we at the GATE Academy, I think we are the first one who is covering comprehensively of whatever new syllabus has been added in the GATE examination. We already have covered fluid mechanics new additions. We have covered that in Hindi channel also, compressible flow. We have covered that in this lecture series also. And now we are covering this steam turbine and gas turbine. So whatever new syllabus has been added in GATE examination 2020, as far as thermal sciences part is concerned, we are going to complete it in all respect by the end of this series. Okay, so please like and subscribe with the GATE Academy. Do motivate us. Okay, please, your comments, your feedbacks are very much important. If you want, you can also write to us. You can also write us on the address, on the mail ID given here. You can go to our website and can have the updates about what courses are running, what are the recent updates on GATE examination. Okay. So please like and subscribe the GATE Academy English channel, as well as go and find and like GATE Academy Hindi channel, so that we can put more videos like this for you. Okay. So if there is any doubt, you can ask me. Otherwise, we are going to conclude this session, and then we are going to meet again in an hour for the next session of the steam and gas turbine. And there we are going to almost complete the part of the steam turbine. All right. So if you have liked the lecture, please write in comment. Please give us your feedback. If you didn't like something, please write that also. We will take it as suggestion and we will try to improve. Okay. So thank you very much. We'll meet again in the next session. Thank you.